Good morning, good afternoon, and good evening to everyone joining us from around the world to today's international webinar, co-organized by EUPD Group and our esteemed partner, Pylon Technologies. We are here today to explore a highly relevant and fast-evolving area of energy storage, the remarkable environmental adaptability of commercial and industrial liquid cooling energy storage systems. This session today will provide a detailed insight into why this topic is not only timely, but absolutely essential as we navigate the challenges and opportunities of the global energy transition. Pylontech, our co-host and one of the industry's leading energy storage solution providers, brings together deep expertise in electrochemistry, power electronics, and system integration. With a strong global presence, they have earned a reputation for delivering reliable, scalable, and robust energy storage solutions. In particular, their work in the C&I segment has been a driving force in boosting energy efficiency, reducing operational costs, and supporting grid stability. As the need for energy efficient management grows worldwide, C&I energy storage systems are proving to be a key in balancing the supply and demand. Among these, liquid cooling systems stand out due to their superior thermal performance, precise temperature control, and the potential to significantly extend the battery life. These systems have not only become a focal point for innovation, but are also experiencing rapid market growth and application diversity. Today's session is based on the findings of the newly released white paper titled High Environmental Adaptability for Commercial and Industrial Liquid Cooling Battery Energy Storage Systems, which was developed by Pylontech in collaboration with the TÜV Rheinland. We will hear directly from our expert speakers, Dr. Kamil Smili, Chief Technology Officer Germany at Pylontech, as well as myself, as we examine the latest developments, technical challenges, and future potentials of this exciting field. So, thank you for being with us today. We are excited to share insights, exchange ideas, and do learn together. Now it is my pleasure to hand over to Kamil for his deep expert insights on why high environmental adaptability matters in C&I energy storage, as well as the current developments and challenges of C&I liquid cooling ESS. Thank you in advance. I'm happy now to hand over to Kamil, and we all look forward to a very insightful session today.
Thank you, Daniel, and good day, everyone, and thank you for joining us today. We are living in an area where clean energy is no longer just a goal, it is a necessity. And as we are undergo a global energy transition, energy storage has emerged as a backbone technology in balancing supply and demand. Today's focus is on a particularly dynamic and promising field, commercial and industrial liquid cooling energy storage system. These systems are becoming the gold standard for thermal performance, efficiency, and adaptability across demanding industrial environments. Let's move to the next slide if it works. Great, it works. So today we gather to discuss a critical aspect often overlooked in energy storage system, how drastically different operating environments create monumental challenges for safety design. While the importance of safety in ESS has gained widespread recognition, the profound implications of environment diversity remain significantly underappreciated. As energy storage deployments scale across terrain and climate, from coastal port to mountain ridges, and from blistering desert to seismic zones, adaptability is no longer optional. Systems need to work reliably, no matter the location. The adaptability is what differentiates a lasting solution from a costly failures. And that's why we are going to go through this slide. Great. Let me illustrate this with two devastating examples. In March 2011, when the magnitude 9 earthquake struck Fukushima, Japan, we witnessed how conventional ESS design failed catastrophically. Seismic shocks deformed battery racks, compromised containing structures, and triggered cascading failures, not because of technical deficiency, but due to the insufficient environment adaptation in design. A decade later, in August 2021, Hurricane Ida's with 150 miles per hour wind and storm surge unintended Louisiana energy infrastructure. Post-disaster analysis revealed that 63% of damaged storage systems suffered saltwater corrosion in electrical components and structural fatigues from wind loads. Failures roots in inadequate environment resilience planning. Let's move forward to more explanation. So at Pylontech, through 15 years of field-proven experience across 90 countries, we have systematically summarized environmental challenges across various regional scenarios. In coastal area, for instance, high salt spray environments severely corrode circuit components of products. This not only because abnormal system operations, but may even directly lead to system short circuit, creating major safety hazards for energy storage equipment. In wilderness regions, direct sunlight and high temperatures significantly impact system charging discharging efficiency, while wind-blown sound can infiltrate product interiors. This compromises heat dissipation and ultimately leads to system failures. In industrialized zones, environmental humidity, temperature, chemical contamination directly affects normal product operations. In urban environments, fire resistance and ventilation capability becomes critical priorities. For data center, for instance, electromagnetic interferences presents a new challenge for energy storage system operations. Therefore, facing these specialized requirements arising from diverse complex environments, how shall we address them? And I want to provide you some more example on how it's coming. All right. So the major topic is here, how we can increase the lifespan of the whole system. So we focus mostly on two major parts, the material selections and the process optimization. Why we move on that topic is just to make sure that even if we have chosen the right selection of the materials, we have to make sure that this can be processed in the production line and in the mass production lines. So first of all, after reviewing all the challenging and the environmental condition, then we select the materials for the energy storage system, and which must take into account the environment aging factors varying across different countries and the region. This is the first step. Based on this, we have to make sure that the design and the manufacturing process must ensure that the system structure remains stable under long-term exposition to harsh environments. And these two parts, they are very important just to make sure that we can move forward and to set a reliable system. Move to the next slide. Have a delay between when I click on it and when it appears. Try again. Yes. So I will provide you here a clear example what kind of environment challenges we have to face. The first one is a high temperature environment, and the second one is a very low temperature environment. And for the high internal activities and temperatures, speed up battery reaction, which increase the thermal runaway risk. For that part, we have to understand that the battery, the whole system is acting, but from the whole system to up to the cells level. So we have not only the system complete with the BMS, with the EMS, with the rack, with the cells. We have also to consider the whole system on that part, which is actually a quite big challenge in this case. Same with the low temperature environment, what we have to increase battery resistance may trigger a lithium precipitation, which is a very important part just to make sure that the cells can also be running during this part, and also which also may increase the short circuit risk. So here we have some natural disaster. For instance, we have here for the headquarters that I already highlighted before, that the energy storage equipment may be displaced, may be damaged, or even toppled due to the seismic forces. And these have to be also taken into account when we make some simulation on the whole structure. That means on the material part, but also on the design. So the battery module should suffer internal structure damage and increase the risk of short circuit that we have to avoid. Regarding the strong winds, this is the energy storage equipment support may bend and break, while snowstorms and heavy rains can lead to deformation of the equipment, housing and electrical short circuits. So for the next factor that we have, what is highlighted as all the factors here, the high altitude area, the storage equipment needs insulation, specialized of batteries and heating measures. Coastal zoning corrosion resistant is critical. For mountain region, robust mechanical structures is required. This is all kind of information that we have to collect it just to make sure that we have the right materials part, the right design, and to design the right solution, even for the sales part. Now, I will review the current development of challenging in our design. So, how we try to face this challenging? The first part is to have a clear temperature control of the technology. This is one of the most important parts, which is directly linked to the two others. Sure. So the liquid cooling system dynamically adjusts coolant flow and temperature, ensuring stable battery temperatures, which is very critical in that part. We have to make sure that we can control the temperature, not only to measure. The structure design, which is the battery pack, use high-strength, corrosion-resistant shells with sealed components to block contaminants. And one of the most important part also, this is the intelligent monitoring, just to make sure that with the BMS and the environment monitoring system, like energy management system, for instance, and all sensoric, the system can work together to ensure the safe energy storage operation, whatever the environment. Now, okay, so how we did this? So when we have listed this part, we have to make sure that we can also make it as a product. So the challenging of extreme temperature adaptability in a high temperature with the liquid cooling heats, dissipation declines. We have to make sure that when the temperature is high, we have the opportunity to reduce the temperature on the cells level, not only on the whole equipment, but even on the cells level. And in lower temperatures, the coolant thickness, which is important, liquid part, impairing the flow and the startup. I will show you some example in the next slides, then you will understand better what does this mean when you have a very high temperature or even when you have very low temperature, what are the consequences of the whole system and when you can start to work with the system and how to have to prepare the system that can be worked on the time that it demands. For the structural strength challenges, the temperature differences can cause material to expand or become brittle. Here, the major part is just to make sure that we have not big differences during the system on the temperature level. The humid environment can lead to corrosion, as I already highlighted before. The system must maintain stability in the regions with frequent season activities. This is what I will show you also with some example that you can understand better how we can move forward on that topic. We have a clear picture what the system should face. Snow and ice launch present significant challenges. This is also mostly on the mechanical structure in that case. The applicability of standard and norms, that's also one of the major challenges that we have to face. Even if we found the right materials and the system and design, we have to make sure that we can pass all standard and norms just to make sure that also the product can be is applicable in different countries. So the lag in updating product design standard is also one part, and the challenge of a regional and industrial standard differences. You will see that the overview of the whole norms and standard in different countries is also a challenging part for a manufacturer like Pylontech. So I'm trying to move forward. Okay. This is one product that we provide. This is the L260 Omni. So this is a cabinet solution which has a liquid cooling system with the IP55. We have a deep of discharge of 95%. The voltage range is between 700 and 936 volts. And here, this is a 1C charge and discharge solution that we provide. This is a whole system with above 8,500 cycles life. And all here, this is a standard that we have to fulfill and that we also pass. As you can see, this is only here the battery cabinet solution with the whole solution on the liquid system with the sensoric, the BMS also integrated, and also the EMS if you recreate it. Another solution with higher battery capacity, this is a L417. This is here a cabinet solution also for outdoor. We have also the same for indoor. This is still the liquid cooling product with a DOD of 95% and the voltage above 1000 to 1497 volts. The cycle life is always above 8,500 cycles, and we still have the 1C charge and discharge solution. We sure provide the certification for countries that need such solution. We have also bigger solution like here container solution wise. This is a L5000 bat for the battery. So we have also here the liquid cooling. The DOD is the same, 95%. We still have here 1C charge and discharge. And here we still have the 8,500 cycle lifetime. All the certifications also. This is coupled directly with another small container for the inverter for the PCS. It can be also directly linked to our battery system. So here is only the battery. And I will give you now some clear example what kind of tests we proceed. I'm trying to move forward. Okay. So this is actually what Pylontech liquid cooling CNI solution with the intelligent temperature control. So the most important part is actually the adjustment functions. So on the hot start and cold start function, which I will provide you some example and some measurement that we did. The precise temperature control, which also very important just to make sure that we have a very low temperature differences between the highest cells temperature and the lowest cells temperature. And this is something that we have to control. And sure, also this is to have the low power consumption on the operation, just to make sure that our solution is not energy consuming, but is actually just providing the energy to the system for the customer. So let's move to concrete examples. Okay, here you have 4 different diagram. So this, what you can see, this is the intelligent temperature control for 4 different applications. So let's start with diagram number 1 with the cell temperature curve. We started the system with -25 degrees Celsius. We started with a power of 0.5. We started with a cool start, and then we make a charge and discharge. So what happened actually here? So we started here during the cold start phase. This is in the phase number 1 here. The lowest temperature of the battery cells increased from -25 degrees Celsius to above 10 degrees Celsius. And we need for this about 11 hours. So the system is designed that even if the system is by the cells has a temperature of -25 degrees, the system will heat up the cells till 10 degrees Celsius to make sure that we can here start to work and to provide the energy to the customer. So the phase 2, in this case, this is the differences, this is the operation part, and this is the the difference between here, the lowest curve to the above curves. This is the lowest cells temperature and the highest cells temperature. And as you can see, the difference is very, very low. We have here less than 5 degrees Celsius between the highest cells temperature and the lowest cells temperature. So just back to the number one, which is very important, is this: during the installation phase, the liquid cooling took about 2 hours each time to hit the lowest temperature to the battery cells, from -10 to 13 degrees Celsius. And then we start to heat after the interval of 2.4 hours. So just to make sure that here we have actually two rounds: the first round of charging and discharging, and the second round of charging and also discharging. This is what you can see in the low temperature test from the -25 degrees Celsius. The maximum temperature differences was 7.2 degrees Celsius from the minimal cells to the maximum cells temperatures. And in the highest test, I will show you later, you will see that the temperature is a bit higher. So number one, this is a heating up. The number two, this is when you are ready to have the temperature for every single cell that they are aligned. And then we start here on the number three. This is the charging part. So you can see that the temperature of every cell is increasing because they are running and providing the energy. And then the number four, this is a decreasing part, what we have actually stopped to work on the charging and discharging. So this is what happened when we start from -25 degrees Celsius. So the number two is the cell temperature curve. When we start with very high temperature environment, we still have the maximum power of 0.5. So here you can see that on that case, by starting, the minimum cell temperature and the maximum cell temperature have a difference of 10 degrees Celsius. So the maximum is 45, but the minimum is 35. Then we have to make sure that we can move forward and have actually a regulated temperature and not so big differences. So we start here to cool down the system. So it's very, very fast here in this case. It's less than actually 2 hours, about 3 hours. And then we can start running the system by cooling it down. So what you can see is that we have here about less than 5 degrees Celsius differences between the minimum and the maximum cells temperatures. And then we cool down the whole system even lower than 20 degrees Celsius. So now move to the highest and lowest temperature of the battery cells during the two charge and discharge. So we make 2 cycles in this case. This is what you can see. I'm not sure if it's quite clear, if you can see the red line. So let's move on that part here on the number 3. So we started with a temperature of 25 degrees Celsius, and then we have a 1 charge effect in this case. So that's what you can see. This is the maximum and minimum temperature difference, the differences of the temperature differences of cells level. So when you move now to number 4, we have here the maximum and minimum also. So on this part here, we have the charging level. So the power here is 200 kilowatt. And then you see that the temperature is increasing. So you have the difference of the temperature between cells. Then here we are discharging. We are still using the energy. So the cells is still increasing. Also, the temperature here on the right side, this is the cells temperature that you have. And the maximum that we achieve is 45 degrees Celsius. While here, the minimum that we have here by discharging is also about 40 degrees Celsius. So we have something like 6 to 7 degrees Celsius differences in this case. Okay, you have here some clear picture what happened if the system is already at a very high temperature environment or actually a very low temperature environment, and how the system reacts not only to set the temperature of the whole system to the operation temperature, but also when it's running by charging and discharging, and then the differences of the temperature between the minimum and minimum of the cells, they are pretty low, up to maximum 7 degrees Celsius. Great. So let's move now on the design. So what I showed you before is the temperature. So this is the cell design. Now have a look on the structure design, which is completely different in this case uh, from the research and development point of view. So in this case, the Pylontech 2G diagonal lifting simulation that was for the M7, what you can see here, energy storage system, confirmed its structural integrity with stress well below material yield strength and deformation within safe limit. So what you see here, we make different kind of simulation with also the battery inside, the rack inside, the whole system inside, and then here this is a container solution, and then it's all here all about lifting the whole system for installation, for instance. So, and this is what we can see here. So the number two simulation that we had here, this is the wind load simulation. So we have here a container solution, and then we have here simulation when the wind pressure is on one phase. So under the wind speed of 250 kilometers per hour with the wind direction perpendicular to the container side, so it's about 90-degree impact angle, the container did not tip over, which is actually good science in this case. So we make another simulation on the snow load simulation. So the results that you can see here indicates that under a snow load of 150 pounds per square foot, which is about 700 kilogram per square meter, the maximum stress generated on the roof, this is on the roof of the M7 liquid cooling system energy storage, was far below the material yield stress, with both the maximum stress and deformation remaining within the safe limits. That means that here the solution that we provide is covering the standard in different countries. So then we have here for the number 4, this is the IPX6 test and also 7. So the Pylontech container has the IP55 and also the IP67, even of the higher rate requirements. So this is a test that we can proceed in our lab, but also by TÜV, just to make sure that the test is also validated by the third party. So another simulation on the seismic simulation, which is a bit difficult to simulate, but we have some models on that topic. The simulation results demonstrate that the maximum stress experienced by the system under X direction or Y direction or Z direction, so on the three direction that we can have, and the simulation three direction seismic impact is lower than the material's lead stress, providing its excellent seismic resistance. That means that here the whole system is not impacted whatever the simulation has been proceeded. So the structure is still stable and has no impact on the material level. For the transportation, which is also one of the very important parts, because all our products are shipped from China worldwide, then we have here the transportation vibration simulation, which is the ESTA 3E transport vibration simulation, confirmed that the liquid cooling energy storage system stress remain well below 1/3 of the material's lead stress, meeting vibration resistance requirement. So we can see here that we have the highest here point on that level, and that's it. So we, on that part, we can clearly highlight that based on all the simulation that we did, we are actually high above the requirement that the environment can challenge us. Let's move from simulation to the real world, okay? Then to validate the structural durability and environmental integrity on its containerized energy storage system, We conducted a 5,000-kilometer overland transportation test across China, starting from Shanghai, our headquarters, and ending in Zhangbei, passing through diverse terrain and climate along the way. So we put 19 sensors has been installed across the container on main beam material modules and key structure nodes. The sensor collected acceleration, vibration, temperature, and humidity data continuously, and the post-journey inspection revealed that no insulation degradation, stable bolt torque, intact appearances, functional charge and discharge capacity. This test demonstrated that the system could maintain mechanically integrity and temperature stability during long-haul real-world transport. It's a major milestone in qualifying liquid cooling ESS for deployment in remote or challenging regions. The multi-safety design. So the BMS, one of the most important parts, prevent overcharging, over-discharging, overheating, and short circuit by optimizing charging, discharging strategies and temperature control. The system features multi-layer safety protection, including voltage, current, short circuit, and temperature monitoring and minimize risk. 3-level short circuit protection we have, the pack level fuse protection, the cluster level protection, and the system level protection. So pack, cluster, system. We have 4-level software protection. Software feature 3-tier protection with fault alarm classified as level 1, 2, 3, plus an additional level 0 lockout function for enhanced system safety. This is in the BMS. Third, the liquid cooling cabinet complies with industrial standard for stability and safety, furthering safety switches and emergency stops for quick power cutoff. Fourth, electrical safety. The system electrical design complies with the standard of the International Electrical Commission, IEC, and the safety requirements of underwriting laboratories, so UL. The integrated automatic fire suppression system can activate quickly upon detecting abnormal temperature rises, preventing the spread of fire. You have also different sensoric inside the cabinet or the containers to prevent the fire if there is any smoke or hydrogen in the system. Okay. When we design the system and also make all the tests, then you have also to pass all the certification, which is not an easy task, to be honest, but this is something that we have to fulfill. Here it's listed all the product certification for the liquid solution that we provide, if it's a cabinet or if it's a container-wise, to make absolutely no differences in this case. We are using also different cells, so we have to repeat for every single system that we provide. Try to next slide. Okay. So from the R&D, from the research and development design phase to the raw material procurement, the manufacturing process, and even the after-sales maintenance stage, by Pylontech, we actually established a rigorous and comprehensive quality control system. So we started actually with the whole process on the EMS control, which is a very important part, from the troubleshooting and early warning, just to make sure we are not going to produce a scrap product, the intelligent production lines, just to make sure that we are aligned with our standards and also our quality criteria. the automatic logistic control system, just to make sure that our production line is running properly and very fast. And for sure, the production data collection and recording. That means that everything that we produce, it's recording, it's saved, and even 20 years later, we have access to this data, and we can also reproduce also this data. That means that if you have a product that has been produced 3 or 5 years ago, then in the next years, we still have actually the production data of this product, not only on the system, but also up to the sales level. Trying to next one. Well, actually, that's a good news because the challenges are driven innovation and not studying it. So we are seeing a convergence of thermal thermal engineering, material science, and predicting software to make the next generation of CNI liquid cooling of the energy storage system. Not just harder or stronger, but smarter. And as global energy reliability becomes a universal concern, these solutions are not optional, they are fundamental. The journey is far from over, but the trajectory is clear. Liquid cooling energy storage is not just copying with extremes, is evolving the master to them. Thank you for your attention. I'm open for questions. Thank you.
Thank you very much, Kamil, for the very great insights. It was, really a deep dive into the technological advancements of the CNI energy storage liquid cooling solutions. We had, quite a lot of interest, from the audience, which is obviously then, or which resulted in some questions for you. So the first one was referring to the low temperature environment, for the product. So, and the question is, I'm not sure if this was correctly understood. Is the resistance not decreasing instead of increasing?
The resistance is increasing.
The question is the resistance not decreasing instead of increasing? Therefore, I'm saying maybe it was misunderstood of the system concerning the low temperature environment.
I don't understand the resistance. What does it mean with resistance?
I mean, it was aimed at one of the first slides where you were covering the low temperature environment, what is happening there. And I think the resistance of the system is meant, but again, maybe this question was not fully formulated in context. But there is also something regarding the L260 Omni system. So the question from the audience was, what is of this design, the cycle life, for this product?
For the cycle lives, they are always above 8,500 cycles. Wow. All liquid cooling system that we provide. This is this is for the 1C. Then we have also to understand that the DoD is 95%. Okay. And the cycle life, what is a very important part, is how many times the cycles appear per day, but how long is the waiting time between one cycle to the next one.
Okay. Yeah, thank you for answering that. We have one concluding question, and this is there not enough spare at the lower and upper limit to keep the capacity at 100% DoD?
So the 100% DoD is possible. The major problem that you have is that uh, you will have a very strong and fast degradation of the system. Uh, Not only on the whole system, but also on the cells level. Uh, that's why if we want to provide the 8,500 cycles warranty, we need actually to make sure that we have actually the DoD of 95%. So most of the time, the lowest would be 5%, and the highest is 100% in this case of the SOC. So this is actually the range where we work with our system. We have some customers, they actually don't go up to 100%, they go a bit lower, so 98%, and they go like 5% on the lowest SOC level.
Okay. Yeah, thank you also for answering that question. You see, there is a strong interest, yeah, in the product line in this innovation. And yeah, we highly appreciate your sharings today. And yeah, looking on the time, I think we have perfect timekeeping. 10:20. It's now my turn to yeah underline a little bit of yeah what you already said in terms of CNI developments. And I'm going yeah to take over at this stage and share some yeah data analytics on how we see the European solar and storage markets evolving. So I'm going ahead now and share my screen, and everyone should be able yeah to see it right now. So yeah, as already introduced in the beginning, my name is Daniel Fuchs. I'm the Chief Customer Officer here at EUPD Group, working in the industry for the last 15 years in the solar coaster, how we call it. But yeah, at EUPD Group, we are extremely committed, excited to boost the energy transition on global level through really in-depth market research, through advisory services, through certification, as well as improvement services in form of branding, marketing, etc. So yeah, my presentation today for you is titled Assessing Europe's Market and Developments for both solar as well as energy storage. So yeah, when we look at the first slide of my presentation, I'm showcasing the annual installed solar PV capacity on a European level. As we all know, yeah, the last 12 to 18 months in Europe have been quite challenging. And although the newly installed PV capacity broke another record last year, yeah, we see that the growth curve is flattening with only 2% we saw from 2023 to 2024. Yeah, we have a lot of reasons for that. It is shown as a really nice duck curve or S curve, how we call it, that speaks on the one hand for market maturity, but also in the same context indicates that there is a fierce competition going on. And looking throughout Europe, we are quite fragmented with 30 countries here that we do have yeah, geopolitical conditions lately that are not, yeah, let's say, extremely pushing the deployment of renewable energies. When we look on the year running, 2025, we see this trend, a very slight growth of the European markets, yeah, continuing. And you see it on the in the last bullet point on the right side. We expect between 66 and 69 gigawatts of new PV deployments throughout whole Europe this year. Now let's yeah take a look more on a country level. And we see that out of the deployments, we had approximately 65 gigawatts. Only the top 10 PV markets last year installed 54 gigawatts of this capacity. Nevertheless, also here we see very diverging trends happening. For instance, in Germany, after the huge boom in the early 2020s, or 22, 21, 22, we saw a slightly reduced deployment growth, with only a couple of 12%. Yeah, we see it near the flag. But also we saw a few setbacks for Spain, Poland, and the Netherlands, as well as Austria, who saw declines of 13%, 11%, and for the Netherlands, even 29%, in the PV installations in the last year compared to 2023. But let's not underestimate the newcomers as well. Yeah, we see their countries now surging in terms of PV deployment, especially France, Italy, Greece, Portugal, and Romania were highlights in 2024. And there are more emerging markets coming towards the gigawatt circle in Europe. And we have here on our radar clearly Lithuania, Ireland, as well as Estonia, which shouldn't be really underestimated. So why is this happening? Or let's say some reasons. We see for sure, and this is now the underlying data-based fact, what Camel from Pylontech already said and underlined with the CNI commitment. We are focusing here on the European level, and we split it down to a segmental level. And as you can see here, it's quite granular, with residential, and then in the CNI space, we even have 4 different metrics. And then we have the utility space. So why is this segmental shift happening? For sure, we see that the countries with their climate targets, ambitious climate targets, have to meet these. There is still a shortage of workforce in some countries in the residential segment, and we do see economies of scale coming that do speak for larger systems. Also, I mentioned it before on the slide. There are fear factors that also should be taken into consideration in terms of geopolitical changes, lacking incentives, etc. So when we look on the comparison between 2023 and 2024, we see that the CNI segment rose from already 37% to 45%, and the utility scale segment from 25% to 27%. Obviously, as this is a 100% bar chart here, we saw a slight moderate decline of the residential segment for PV of 8% from 23 to 2024. Now we are looking on the storage side of the industry. And here we see the deployments on a country level. And only the top 10 storage markets in Europe installed approximately 20 gigawatt hours of new capacity in the last year. In terms of the total newly installed storage capacity, still Germany is the driving force within the European Union and even on cross intercontinental level in terms of volume, followed by a surging Italian market and as well as the UK is on number 3. For Italy, as well as the UK, the majority of last year's installations, and we see it later on as well, is coming from the CNI as well as utility scale segments. Utility, especially in the United Kingdom, heavily booming, whereas Germany is still quite dominated until now, I have to say. This will also probably change in the near future by residential level installations. So yeah, this slide I already introduced. We look now, or we assess the countries also more granularly on the segmental level. And yeah, the major, let's say, message here of this slide and what we have been seeing based on the data and our experience lately is that, yeah, the dominance of the residential energy storage segment across all Europe is decreasing. Maybe not, yeah, the dominance is coming to an end. It's still a very lucrative and big business, obviously, in Europe, but it's won't be longer dominated only by residential storage as it was in the past. So across Europe, what does it mean? There are significant investments are now flowing into the CNI and utility scale projects. And yeah, we also see a growing push for increased self-consumption. So all together, combining these dynamics, they are driving profound shifts in the European energy storage market. Also, as PV and storage normally go hand in hand, which makes sense, we see a similar, here on the next slide, a similar segmental shift happening in the energy storage space. Yeah, why is this here happening? We have a pull forward effect because of the conflicts we currently see. As I mentioned beforehand, there's a significant investment volume going in large-scale PV and also storage. There are already grid constraints. Yeah, we need that for buffering, and we also see, yeah, more often negative electricity prices. So yeah, while the share of residential storage is expected to remain unchanged, more or less, the market growth, yeah, in total, here we see it based on yeah, gigawatt hours and it's not on percentage like in the PV slide, is driven by the CNI as well as utility scale segments. And yeah, for the CNI segment, we see or we expect a growth from last year to this year in Europe of, yeah, a massive 60%. So it is uptaking, extremely growing. When we, yeah, then take a really close look into the annual installed CNI storage capacity, here we have selected European countries. Yeah, this is also speaking for itself. Yeah, this is not yet maturity. This is growth. Yeah, we are now in the start of a very big thing in the CNI energy storage space in the very near future, with massive yeah, increases in deployments. And yeah, we see it here also on the right. We have pointed it out. The annual installed capacity is to rise from 700 megawatts in 2021 to almost 11 gigawatt hours in 2028, yeah, across these selected European markets only. This is not whole Europe. The market leaders here are, yeah, let's say again, like in the, as I have shown in the previous slides, this is a forecast slide now, will be Germany, Italy, as well as the United Kingdom. But also, as we see here in our forecasting, some markets do need a further push and lagging a little bit behind. That include Austria, Switzerland, Spain, as well as France. So what is really needed? Yeah, we see a highly fragmented level here on how C&I energy deployments are, pushed by incentives, how they are going naturally. Manufacturers do need to have tailored strategies for each of these markets and should have precise knowledge in order to gain the biggest share or piece of the cake possible in the big markets. So we also, or I will actually conclude here more or less with some voices from the field we have gained. Yeah, this is based on our current commercial and industrial EPC monitor. Yeah, that is out and available for everyone. And we have, as the name says, surveyed and investigated primary data insights from EPC companies. So we see when we look on the barriers, yeah, the policy visibility and uncertainty were the major barriers to the C&I market across all the countries in Europe we have researched. When we go to the drivers, nevertheless, we see this is the upper part, we see conversely country level targets and incentive programs served as the key driver for market growth. Yeah? This is something when a market or a segment is in the early stage is based also on our experience giving the major push in order to increase these segments and deployments there. Yeah, to finish my short impulse presentation today, to underline the significance of what Kamil already mentioned about EUPD research. I guess most of the audience already know us. We are a globally operating company, EUPD Group, focusing on market research, focusing on advisory, certification, as well as improvement in terms of branding. We do have a very impressive global network that we have qualified and continuously expanded globally over the last 25 years of our company existence. And here you see our company group structure. So our major fields of operations are not just energy. So most of you will probably know the renewable energy or smart energy space of EUPD Group. We are also, since many years, very active in the field of ESG. We do have an ESG summit in Germany, a major event, flagship event we are hosting at the end of November every year in Bonn, Germany. And we are also covering a lot of social sustainability parts. So that's our nature, that's our DNA, where we come from. And we work with all the tier one companies together, so all across the value chain. And with that, I would like to thank you very much. I was a little bit too long. With that, I think today's session will be coming now to a conclusion. And once again, also from my side, thank you all for joining us today. On behalf of EUPD Group, as well as our valued partner, Pylontech, I want to express our sincere appreciation for your time, engagement, participation in today's webinar. We very much hope you like the insights shared, especially the keynote address of Kamil around the environmental adaptability of liquid cooling energy storage systems. And a special thanks, of course, also to Dr. Kamil Silmi. Great presentation. We had a lot of engagement. Thank you also to the audience for your questions. And until next time, Thank you once again, and let's continue driving forward the global energy transition together, despite all challenges we are currently facing. Thank you very much.